So again, where and how do I start learning ocean modeling? If you go back to the definition that I gave from Stephen Watermark, it says that it is a representation, an ocean model is a representation in the form of equations and computer code describing the physical process of our understanding of how the ocean works. Okay, so based on that, we want to start looking at the equation aspect of it. We've looked at some of the physical processes. And so, what are some of the equations that modelers have to deal with or work with? Okay, so these are just some points. So to start ocean modeling, you need to get some understanding of the equations of fluid flow, often called the Navier-Stokes equations. So that is where you often have to start from. Even if you want to use a model as a black box, a model that you haven't built yourself, it is still very important to understand the background equations underlying whatever you're doing, whatever model you're using. Learn how to discretize the equations. I'll talk a bit about that later on. That means convert the continuous equations into discrete forms. Understand some numerical analysis, and then you need to know some Python or MATLAB in order to be able to pre-process your data. So Python and MATLAB are often used. So one of the equations that you would come across, okay, in modeling is the momentum equation here. So this basically talks about a change. So think about a fluid, let's say in a box, that is moving around, changing things, build-up of fluid here. It's less dense here, it's heavy there, and it's all moving around like the ocean. Okay, so this says that a change in velocity with time. So that's acceleration or local advection. In other words, if you take a parcel of fluid and then you are following it, all right, the change with respect to time plus if you take the earth is rotating, so this is the rotational aspect of it. This rate of change or acceleration is equal to the pressure gradient term, all right. In other words, if I have fluid here and less over here, all right, the fluid here would like to move, all right. So because there's a gradient, there's a pressure gradient, or if there's a pumping on one side, okay. So this describes that. This describes buoyancy, right? Heavier fluid would like to sink, lighter fluid would like to rise up. So that describes the buoyancy. And if you have external forces like the wind forcing, frictional forces, forces in the surface of the ocean precipitation, these are often described as these external forces. Okay, so force is equal to ma mass times acceleration. Basically, this is a more complex form of that. So this is describing that. This u here is a vector. It consists of the u velocity, zonal, the meridional, and the vertical velocities. This omega here is the Earth's rotation rate, p is pressure, rho is density, and g is gravity, right? Gravitational acceleration. Okay, so that is the moment you come across this. That's all I'm going to say about it. There's a so-called continuity equation, or the conservation, which describes the conservation of volume. All right, if you have fluid in a container and you squeeze it, of course, to conserve the volume, there needs to be this bulging up. Okay, the fluid will have to bulge up, up or down. Okay, depending on the container. And so this is describing that process, and it's called the continuity equation. You also have an equation called the advection diffusion equation, which describes how a tracer, like a temperature or salinity or a dye in a fluid, will be changing with time. And if there are currents, all right, how the change in time, local change in the tracer with time, is being carried around, right? This fluid is moving that tracer around within the fluid, and that is equal to the diffusing is being moved about. At the same time, it is diffusing. Okay, so this describes the diffusive aspect of it. Okay, so this is a diffusivity coefficient. So it's called an advection. It's being advected or moved around by the velocity. Is diffusing because it's a tracer that is being diffused, and this depends on the type of tracer. Okay, so if you have a dye in the fluid, you have the temperature or salinity in the ocean, you need to be concerned about the advection equation, correct? In the ocean, of course, you also have to be mindful of an equation called the equation of state. This is a linear equation of state, which states that density is linearly related to temperature, T, and then salinity, which is S, okay? Alpha and beta here are just the coefficients of thermal expansion and saline contraction, okay? And these constants are just given by these numbers. So, density is related to temperature and salinity. That's the equation of state. So in all, when you see a model, when you're working with a model, you'll be dealing with 7 equations in 7 unknowns, and these equations are nonlinear equations. In other words, these are equations that you cannot solve analytically. You cannot take a pencil and paper, or pen and paper and solve them. They are 7 because you have the 3 from the velocity components, you have temperature equation for the temperature and the salinity, you have 1 for density, and then a separate equation for pressure. So that makes it 7 equations in 7 unknowns, and these have to be solved. Because they are nonlinear and complex, often you solve this numerically. That is why you need some background in numerical analysis, discretizations, and all of that. Okay? So basically that is about the equations. So once you have taken your time to go through some of the equations and have some understanding of them, the next thing modelers often do is that they will discretize those equations. So the equations are in continuous space, right? You have to change them into a discretized form where you can actually put them in a computer, code them up, and be able to solve the equations. So that is called discretization. And in doing that, you also have to consider the horizontal grade. We'll talk about that. You have to consider the vertical grade. I'll also talk about that. And then you have to consider boundary conditions. What are the conditions of the boundary, whether the surface or the bottom of your domain. You have to consider all these things when you are modeling. Okay. So the process of discretization, as I mentioned before, basically takes the continuous equations and then you turn them to a system of algebraic equations. Okay, a discrete set of operations. All right, because that is what you can actually put in a computer, rewritten as a code, and you can solve them. So there are various discretization methods like the finite difference method, the finite element, and then the finite volume methods that are often used. The finite difference is probably the most popular. And these are things you learn in various classes, undergraduate, upper level probably, and then graduate level courses. When you take them, you go through, study some of these methods of discretization. Okay? Just I learned this is an example. LA grade, model grade by Louis Fry Richardson. Okay, so that's what I'm going to say about discretization. So the equations you've seen before, that is not how they are put into the computer. They are discretized first before you do that. And then, as I said, you also have to think about horizontal and vertical grades. So horizontally, if this is your grade, for instance, you can use a regular grade where you use regularly spaced lines, all right? Okay, to split this into various grades, like boxes or rectangles, and then you solve your equations within this. Okay. In the case of global modeling, you can't often use the regular grade because there is convergence at the poles. This longitude will converge, so you have problems when you get to the top here. So people come up with different approaches and various methods by which they do that. Now, one of the clever ways they do that is by using so-called tripolar grade. All right, where you have three. You move the poles to land. And you have 3 of them. You have various complex methods and approaches you can use for global modeling. But if you're not doing global modeling, you can just take a piece of the ocean, like the Gulf of Guinea, and then use regular grade to get it. Okay.